All right, everyone, welcome back to our final workshop of this very exciting meeting. Give you a chance to get your butts in your seats. Our numbers are starting to dwindle as people fly out, but it's okay. The cool people remain. So we were talking about what we're going to do with this document, and an interesting idea came up. Daryl came up with it, and Michael thinks it's a good idea. So as I said, we might have Michael and Saeed Salimpour write an article about what's been going on here, an article about the document, and then just attach the whole document as an appendix, wherever it's published, maybe AER or PRPR. One of these, we'll let them find the journal. They'll talk to the editors, but that's one way that we may get the document published, by just having it as an appendix to a paper that's talking about it. So I thought that was a cool idea. In which case, we'll all be authors on the main paper as well. So that'd be nice. Okay, so we're going to do a little bit more radio astronomy. So I love radio astronomy. What was that commercial? Was it 80s, 90s? The other pork, the other white meat? Was that it? Is that the commercial? Pork? I view radio astronomy, the other ground-based astronomy. So, and no one knows about this, right? Here we have the atmospheric transparency. Of course, you see the parts that have to be done from space, and there's the optical window wavering there in the near infrared. You have some opportunities there in the near infrared as well, but basically the optical window. Nothing for a while, and this is all due to different reasons: oxygen, carbon dioxide, ionospheric scattering, ozone cause all these places we can't observe through. But then you have this really broad radio window. And so great, why don't we make use of this more in our classes? There are lots of reasons why. One of the primary reasons why radio telescopes are incredibly expensive. 16-inch is kind of the standard size, or canonical size for a Skynet telescope. And you consider that a small telescope. But a small radio telescope is like 20 meters. As you'll see in a second, I'll just put it up right now. This is the radio telescope that we have integrated into Skynet, 20 meters across. The largest optical telescopes, up until this new generation of scopes that are being built, we spend a lot of time around 8-10 meter. That's twice the diameter. But this is considered a small radio telescope. This thing's 6 stories tall, 150 tons. It is, for a small telescope, it's much more expensive than a small optical telescope. Incredibly expensive pieces of machinery, and they require constant maintenance, even much more so than optical telescopes in our experience. These things break at least a couple times a week, and we're always working with Green Bank to bring them back up. It's not Green Bank's fault, it's just they're complicated pieces of machinery. So, part of it's the expense, part of it's the remote communications. Civilization makes a lot of radio waves, so they must be in very remote locations, so it's hard for students to get to them unless they travel. And they see things like this a lot. They look like satellite dishes, very similar technology, but being able to use it to do astronomy, it's too expensive for college campuses to have. They're very far away. And us as a community of educators, we just don't have a lot of experience. I mean, I do, and people have worked with me for years too. And I'm not a radio astronomer, but as an educational radio astronomer, over the years, just from playing with these things, I've gained experience, and I've fallen in love with radio astronomy education and using these telescopes. And I hope to bring more and more educators into this so they can share the joy with their students. And it's not like you're doing the same things in optical. They're very orthogonal. You can see the universe in such a different way, different emission processes, that you gain valuable information that only through the combination of optical and radio, and often archival resources like URSA, that you can piece together a complete physical picture of what's going on, which is kind of the theme of our MWU curriculum, going multi-wavelength and painting a more complete picture. Anyway, we're trying to make more of these things available. We've had this deal since the Great Recession with Green Bank. I think we get about 10% access of the uncontested time. Often these small radio telescopes, they sit unused. And we can, all that, if no one else wants to use it, we can use it as much as we want. That's how Skynet works. Uncontested time is free game, doesn't count against you. But in terms of contested time, we have 10% of this. Now with the DoD funding, we're adding more radio telescopes. These are the first 3 that would be integrated. They're run by University of Tasmania. We have the Seduna 30 meter on the left. I think we have like a 3.5% share of that. And then in Hobart, that top one's at 26, if I recall. Is that right, Michael? 26? Yeah. And I think we have 3.5% of that. And in the bottom, you see a 14 meter. It's smaller. They're refurbishing the physical antenna right now, but we'll have 50% of that. That's a 10-year contract. And the Green Bank one's essentially in perpetuity. So after, by 2035, we'll have to renegotiate, but we're also integrating a 12-meter telescope at Perry and possibly their 26s. Arecibo, the big one's gone, of course, but they have a 12-meter educational one. Lots of people have been coming up to me with smaller ones. So once Skynet 2 is ready, and I know I keep saying that, it's like, when will, fusion's 30 years away, always has been, always will be. I'm starting to feel in that mode, but I really think we're about a year away from producing Skynet 2, which is going to facilitate the integration of these radio telescopes. The 20-meter, it's a radio telescope wedged in an optical imaging scheduling system. We can use it now, but it's going to be so much nicer soon. There's just a couple things about these telescopes here. Here's the Green Bank 20 again. And there are big differences, but there are also similarities. That dish there, it's not a mirror. It doesn't need to be. The wavelengths in radio is so big you don't have to polish it smooth, but it's a reflector. It's a parabolic reflector, just like we have on our optical telescopes, sending the information up to prime focus. And one of the things about this is the wavelength. So that first equation should look familiar to most of you. This is the angular resolution equation, the diffraction limit of a circular telescope. 1.22, this is in radians, times the wavelength, divided by the diameter. In optical, those wavelengths are hundreds of nanometers. And so the diameters are the sizes of our telescopes. And you do the mathematics, and you end up with a theta, a blurring scale, due to the optics. That's far less than the blurring scale due to the atmosphere. So we often don't think about it unless you're building something in space. But with radio telescopes, it's different. Yeah, the diameters are bigger, but the wavelengths are way bigger. Instead of hundreds of nanometers, we're talking tens of centimeters. And so I have some typical numbers here that the Green Bank 20 meter has a diameter of 20 meters. We'll be looking at 21 centimeters. That's the H1 emission line, but I put 20 there to make the math easy. And so you plug that in and you get a blurring scale of 0.7 degrees. This is single dish. Now, some of the most accurate, highest angular resolution pictures ever made. You've seen the Event Horizon Telescope, et cetera. That's interferometry. And we're not so bold as to try to integrate that into our student level interface. These are single dish telescopes, and so the images are blurry. And we still do image work, as you'll see, but there are other things you often focus on. Timing, like with the pulsars, and spectroscopy. In fact, spectroscopy, as you'll see, it's far easier to do in the radio than the optical. In the optical, you have to build special instrumentation and then roboticize it and put it on our networks and then teach the students how to process it. In radio, you get a spectrum whether you want it or not. At every observation, every read, you get a full spectrum. And so you could do all sorts of great things like Doppler shift, cosmological redshift, and we're going to do those things today. Okay, let's see. Oh, so 0.7 degrees. We're going to look at some edge-on spiral galaxies. I think there are 7 of them that are close enough that in the amount of time that we're going to use, you can detect what I want to detect. I'll get to that in a second. But I have a sample of 7 galaxies, and they all occupy less than 0.7 degrees on the sky, right? Other than Andromeda, we'll come back to that. Any nearby galaxy you target fits within the beam of the telescope. So these telescopes are terrible for imaging. If I make a picture of this, it's just a blob. but it's great for spectroscopy. We get the whole target in our, what a radio astronomer calls the beam of the telescope. So we shoot the whole thing at once, get the spectrum of all that gas. And so let's talk about that gas. Why do we see it at all at radio? That was an optical picture of the Sculptor galaxy NGC 253, and that's one of our targets that you'll get to choose from. Here's the emission mechanism. It was asked yesterday by Dave. He was showing you the spectra. He said, what's this emission line? And someone shouted 21 centimeters, H1. And so this is the mechanism at play. I apologize, many of you know this, but not everyone, because radio is unfamiliar, so a little bit of review doesn't hurt. In optical, we have emission lines due to transition from orbital to orbital. In radio, you can get them through different mechanisms, but the primary, most important one is the 21 centimeter emission line. And it takes place, it's hydrogen, it's completely in the ground state. There's no transition from orbital to orbital, it's all ground state stuff. You got the proton, you got the electron, they're spinning charges. And so you spin a charge, you have a magnet. And you've played with bar magnets before. There's a configuration where they go together real easy. When they're anti-aligned, there's a configuration where you got to expend some energy to hold them together. So there's a difference between an energy difference between aligned and anti-aligned. And so you have two different energy states in the ground state, and that's something you don't often teach in the most introductory courses. And it's very easy to excite. You just jostle the hydrogen, bump it, give it a little bit of energy, gets excited. The half-life's pretty long. It's 11 million years, but there's a lot of hydrogen out there. It's usually a whopping bright, screaming signal. And it produces a radio photon of 21 centimeters, 20.4 megahertz. So that's what we're going to target, because if you're doing Doppler work, you really want an emission line, or an absorption line. Okay, it's most of my setup, except it's always good to think about what are we going to see before we look at it. You hypothesize and then see if your expectations are met. So we have this emission line coming from cold hydrogen galaxies. Spiral galaxies are full of cold hydrogen, and we're going to be looking at a sample of edge-on ones. So what are the two primary things that we can detect using this line? Anyone want to venture? So intensity, we're not going to worry so much about that, but absolutely broadening. Broadening, that's one of the key things we're going to do, because since the whole galaxy fits in the beam, the left side of the galaxy, we're going to detect the right side. And one side's rotating towards, one side's rotating away, so it's broadening. You poke through a hole of the Milky Way, and you get a very narrow line. But from the Milky Way, you get a whole galaxy in your beam, you're going to have a broadened line. That broadening will give you the mass. And so we'll weigh some galaxies today, including this one. And what's the other thing you get? The shifting, the Doppler shift, or the cosmological redshift. When we look at Andromeda, we'll come back to that special case. It's bigger than our beam. Yeah, that's just traditional Doppler shift. As we all know, Andromeda is moving towards us, very little lateral motion. We're going to smack each other in about 3 billion years. You can calculate that from just taking a spectrum of Andromeda and seeing the shift of the line, and our students do. But for these other galaxies, they're outside the local group, and so they're all redshifted due to the Hubble flow. And, we use the Doppler shift equation, but it's not really a Doppler shift. It's the expansion of space and the stretching of the waves. So you can measure Hubble's constant. We do this even in our Opus capstone lab. So we'll do kind of a mix of these two things. Okay, that was the setup. I'll put this down, though there'll be a couple more images in a bit. Let's go to that same tiny URL that we had before, tinyurl.com/skynet-workshops. I'm going to show you how to put in a spectroscopic observation. You're all going to pick a galaxy. I'll let you get here first, and then I'll show you where to go. Let me put that. Yep, you're all popping in here. I'm seeing all these weird animals. We got a duck, a blobfish. That's cool. And I don't know what that is. Axolotl, a cheetah. I'm not going to, I give up. Some of these I don't know. Clearly, it's a good thing I wasn't a biologist or a zoologist. Okay, so log on to this page. Everyone pretty much there? I'll give you a second because if you don't get to this page, then you won't get to the links and you won't get to do anything fun. If you want fun, you have to go here. Oh, plus 42. There we go. I was saying only 5 people. Come on. But there's 48 of you. So here we go. Okay. And scroll down. This is the stuff we did before, the pulsar stuff. Somewhere down here, we have radio astronomy, Doppler spectroscopy, and imaging. I point out this, here's the MW guide. The Hubble constant stuff, we do a little bit in here. We also do it in the Opus course. We even have a CMB part of that unit. But that's the MW guide. Again, this stuff is still being developed, so it's not pretty looking. It's in a Google Doc, but it's there if you want to try this stuff later. Okay, next, I want you to pick an edge-on spiral. Now, I've tested a whole bunch of galaxies, and this is, which ones can I detect the H1 signature with a 20-meter telescope? Clearly, clearly these are, bright, nearby galaxies. So pick one. Now, a little bit of qualification here. 4 of them are easy. It'd be real easy to see their H1 shifted and broadened signature. But if you're up for a challenge, there are 3 more that we can do. We're going to do a 10-minute integration on, 10-minute off. And we'll put them in the system, and you can check your data later. Then we'll look at some archival data to see how to do the analysis. Everyone's picked one? You know the one you want? Okay. Is that yes? Everyone has their favorite spiral? Okay. Let's go to, I even have the fun names here, but also take a look at the technical name. You're going to need the technical name to search it in Skynet. So go to Skynet. Here we are. My observatory. Just like with the pulsars, we're going to go to radio observing. And we're going to, am I going too fast here? Skynet, radio observing, add a new observation. Under that list, under radio observing, you probably see your pulsar stuff. Most of the pulsar observations have come back. Don't look at it now. We're busy, but a little bit later. So we're going to add a new observation here, and just type in your target. I'll do NGC 253, the Sculptor Galaxy, which I had up there. I'm going to search it. Okay, and it's found it. If I scroll down, here's the observation name. Again, you can edit it if you want. There are the coordinates. And these are just generally good numbers. You don't want to be more, we can do radio astronomy during the day. I didn't mention that. I think most of you know that. If you get too close to the sun, it starts bouncing off the support struts for the receiver and can mess you up. So I'm saying, we're not going to image if we're within 10 degrees of the sun. And you want to be about 20 degrees above the horizon because the horizon emits thermal radiation, which you can detect. At the end of my summer program, we all stand in front of the radio telescope and do a group picture. And there's enough of us standing in front of the telescope, it detects our thermal emission, which is kind of cool. Anyway, yes. Oh, I was going to say, yes, the air mass chart doesn't work in the radio. I guess it does. I guess my programmers fixed something that I requested. That's miraculous. Okay, and so this one, it's kind of low in the sky. I'm not going to get my data back for 14 hours, but that's okay. Save and continue. Okay, now we got to make a little change to the receiver settings. Before you're doing broadband observations, getting in a whole bunch of frequencies to detect that pulsation. Here, we want a high-resolution spectrum focused on the 21-centimeter emission line. So the thing you want to change from low-res to high-res. And you don't have to, but I kind of recommend you change the frequencies. What's going to happen? It's going to take 2 spectra. These spectra are 15.625 megahertz across. I'll just show you here. In low-res mode, we're bringing in 80 megahertz. In high-res mode, it's a much smaller frequency range, and it's actually going to be 2 of these back-to-back. And these are where we center them. I recommend centering the first one on 1403 point. Doesn't really matter that much, but I have 0.375. And the second one has to be 15.625 megahertz away from it. These 2 spectra are back to back. They're adjacent. That's just how the hardware works. So that means this one's at 1419. And that's the one I'm really interested in. Again, the natural frequency of H1 is 1420.4. And so a lot of our targets are going to be redshifted to lower frequencies. And so setting the second frequency range to 1419, often your redshifted emission line will be in that second spectrum. And this one is set simply to be 15.625 megahertz away, so it knows what to do. I'll just give you a second there to enter those numbers. This is akin to, on an optical telescope, the filter page, where you pick, I want red filter, I want green filter, I want H alpha. Here we're picking our frequencies. It's all done not through a piece of glass in front of the radio telescope, but in the electronic post-processing through local oscillators that they beat against the signal, getting differences that can work in electronic equipment. Everyone good here? Okay. Save and continue. There are all sorts of great lessons there. You could have a whole class on how radio detectors work, et cetera. Okay, I have a lot of time credits. I'll pick one. And the path type, we're going to do what's called an on-off spectrum. Now, if you just want to see hydrogen 0.1 centimeter emission in our galaxy, you don't have to do anything fancy. You can just do a tracking observation like we did with the pulsars. You track, you integrate the light for like 60 seconds, and you easily see the H1 emission in our galaxy. These galaxies are farther away, so we have to do what's called an on-off spectrum. And you'll see why in a second. We'll get it submitted, and then you'll see why. So what we're going to do is 300 seconds on target. The path type should be on-off. Yep. Okay, we're going to do 300 seconds on target. Then we're going to switch over. Let's just move 2 degrees in right ascension. It could be 0 degrees in declination. Just shift over to the side. You know, our beam is 0.7 degrees, so I want to get, you know, much farther than that. Not super far away, but farther away. So a 2-degree shift off to the side. And then it will do another 300 seconds of off. The line is really faint, and you only see it by subtracting the off from the on. We don't need any repeats. Integration time doesn't matter. All the rest could be the same. So it's an on-off spectrum, 300-second duration, then a 2-degree shift, and you can save and continue. You ready for me to press the button? All good? Okay. So I'm going to press it and then just submit it. It was not a difficult, oh, yes. I will show you with actual data. It'll make more sense with actual data. I just wanted you to get your observations in. On the optical side, we have something called linking. If everyone observes the same thing, it observes it once and shares it. We don't have linking on the radio yet. It will be in Skynet 2. So it's going to take, what was that, 10 minutes for each of you. It'll be a day or so before we get through all those observations. So don't expect it back right away. Check back in a day or so. But I have some that have already been completed. So if you go back to the document here where you picked your target, scroll down, here are the settings that we just typed in. So if you don't remember them, they're right there. But then down here, results should look like this. So whichever galaxy you picked, like I picked Sculptor, it's easy. But some of you were up for a challenge. Whichever one you pick, go ahead and click on it. I'm going to click on Sculptor and open it up. And this is an example of what your data will look like when it comes back a day from now. Okay. Now, this is the same page. These pages are made by Green Bank Observatory. We'll have our own versions in Skynet 2. And it's the same thing that you saw with the pulsar. Here you have the light curve, and here it's on target for 300 seconds and then off target for 300 seconds. We don't see any pulsing here because we're not looking at a pulsar. But what's really interesting is the spectrum. This is the spectrum, but this is the on-off spectrum. Let me start by showing you the on spectrum. Down here, you can see the on spectrum. And so you see this blip right here? That is not the hydrogen emission from that galaxy. That's the hydrogen emission from our galaxy. We got to look through our galaxy. That's going to be the brightest thing. The hydrogen emission from that galaxy is this little slight raise right here. That little blip's interference. Don't worry about the little blip. See how it kind of comes up just a little tad? Easily missed. You would never see that. Now, the broad oscillations, that's not astrophysical, that's instrumentation. The electronics or radio detectors are pretty tricky. Those broad oscillations, it's just due to the processing. So we're looking for stuff riding on top of that. But that's too subtle to measure, so that's why we do on-off. If I click on the off spectrum now, you may notice that tiny little raise is gone, okay? And there's the Milky Way hydrogen, and there's that interference there. Okay, so what you want to do is on minus off. It cancels everything out, and actually it's on minus off, and you divide by off. That wavering is like a throughput. And so you divide by it to flatten the spectrum, get equal throughput. And that's what you're saying here, on minus off, divided by off. You subtract out those broad oscillations. They'll still be there a little bit. The hydrogen line is right here. I did not get a complete cancellation. You won't get a complete cancellation. These other little spikes are RFI. Here's the key feature. Again, this is an easy one. This is Sculptor. And so here is and it's broad. As David said, it would be broadened. So here you see the Milky Way hydrogen, very narrow, because we're just poking through one spot. It has one redshift. But here, this is a whole galaxy with a bunch of redshifts, so it's been spread way, way out. And so this is the higher frequencies on this side, so that's the blue shifted side of the galaxy, and here's hydrogen from the red shifted side. And if you go to live spectrum, you can zoom in on it. And if you're doing one of the difficult ones, I'll walk around and help you. But there are two numbers I need you to extract right now. Come on, Greenbank. It does take a moment to load, though. I don't know what happens to their server. There we go. So once you load it into live, you can come down here in the lower left. There's a magnifying glass. And remember, I told you you're taking two spectra. Here's one spectrum, and then this one connects right here, and this is a lower frequency spectrum. I'm not interested in that. I'm just going to draw a box around the line here. There are two things I want. I want the central frequency. Just kind of eyeball it. Come down here, and for me, I got, 1419.3 for the central frequency. Remember, it emits at 1420.4, so this thing has moved to lower frequency. It's redshifted. Measure that for your target, whichever target you picked. Measure the central frequency and then measure one end. This is going to help us with the rotation aspect. So the left end here for me is around 1418.4, or the right end around 1420.2 maybe. I want you to make these measurements. Now, that was an easy one. I'm going to bring up a hard one just to give you an idea. Here's a tough one. This was the third one on the list. What was that? The surfboard galaxy. And it's right here. This tiny little comes up, plateau, and comes down. That's it right there. We can't see it on the red one. We didn't get enough cancellation, but you can measure it from the green one. I'll give you all a moment. Measure those two frequencies from your spectra, the center and one edge or the other. If you can't figure out where it is, if you're doing a difficult one or an easy one, call us over. We'll help you out. Reed knows how to do this. He can help too.
Hard one. I don't see it.
It's right
Oh, I was way
here.
off there.
Yep.
Okay.
And this one's riding on a gradient, but you can see up, over, and down. And the green one, And you often get this horn-shaped structure, not always, but you often get a horn-shaped structure if it's an ordered spiral. It's a limb effect. On the limb, you're getting more stuff. Yep.
Is that easy?
It's this whole
Zoomed in.
thing. It's this whole thing. It's a little bit lopsided.
This?
Yep, your center is here, and there's an edge, and there's an edge.
All right, so this edge,
Yep.
for both the red
Yep.
and green. And then center would be like.
Center right there. That little spike, ignore it. That is either instrumental or radio frequency interference at a particular frequency. Yep. Yep. So this one does not have good ordered motion. So instead of a horn-shaped profile, you get a Gaussian. But you can zoom in using go to live spectrum. And you can click on the magnifying glass, draw a box around it. Here, your hydrogen, you have two hydrogen lines in this one. What was this, Bode's galaxy? Cigar, yes, cigar. So you're looking through two arms of our galaxy. If anyone picks cigar, you may see two Milky Way spikes because you're looking through two arms of the galaxy with different redshifts. Yep, the middle and then one edge.
One edge?
Yeah, one or the other. Either will do. The frequency is. Yep, you kind of have to eyeball it and estimate. That's okay, neither am I.
So measure like this and this, or
Yeah, this one. So
which one, the green or the red?
the green, it's sitting on a slope. You can see the same pattern, but it's on a slope, makes it tougher. But I'd go with the red in your case here. The middle is, go ahead and zoom in. Grab the magnifying glass. Draw a box around this stuff here. Okay. There's your middle. There are your edges. Mm-hmm. And yep, it should be an elevated plateau essentially. This galaxy is a little lopsided, so you're getting more gas rotating away from you than towards you. Yep. Which galaxy is that? The Whale. The Whale, I don't know if you're familiar with that galaxy, but it's a bit of a mess. Yep. Y'all making progress on your two frequencies? Having any difficulty? Don't be shy. That is incomplete Milky Way cancellation. Here it is right here. Yep. Yep. And that's probably interference, or actually in the center of the spectrum, the instrumentation always just gives a spike. Electronics can be tricky. Yep, the Milky Way hydrogen won't cancel completely. It'll still be the strongest feature.
So it just took this just now.
Oh,
I was the first one to get on,
okay.
and it looks nothing like.
Which galaxy is
That
this?
was the surfboard.
Oh, that one up there? Oh, it's a tough one.
But I found exactly.
Okay, it's right there. Now let's look on yours.
Here's mine. It doesn't look anything like that.
Okay, go to the live spectrum. Let's see if we can, the red one looks kind of messed up. Scroll down and find your magnifying glass. And do a long, skinny box just around the red. Let's forget the green. Well, I think that's it, though. Again, this is one of the difficult ones. So you may want to do more than 5 on, 5 off, but that's probably it right here. Is that one of the easier difficult? Yep, it's right here. See it there?
Yep.
And so you can get the magnifier, draw a box around those. Reload the page and that'll fix it. Yep, just right there. You may have to hit the magnifier again.
There.
Keep going. Yep. Well, that's plenty. Yep, right there. So it's coming up. There's your, it's right here. So there's your center. There's an edge. So write down those numbers. Is everyone there? Anyone need another minute to get your two frequencies? Anyone need more time? Okay. Got your two frequencies. So I think it's in the, yep, right here. Scroll on down, tinyurl.com/skynet-spirals. Let's do some measurements. And then we'll do one final fun activity here. So go to tinyurl.com Skynet-spirals. You see it right here? It's right below the ones you just picked from. It's a spreadsheet. Now, before you start typing your names in, look at the tabs on the bottom. Different galaxies have their own tab. So find your galaxies tab, sculptor, cigar, surfboard, whatever. Find your tab and stick in your name. And hopefully we have a couple people on each galaxy so you can check your results against each other. Or embarrass yourself against everyone else who did it right, okay? Now, let me just say, normally I would not give this to my students. I would want my students to make this Excel spreadsheet, but in the interest of time, I did it ahead. Here's what's going on. Stick your center frequency in the first box. And here we're calculating the line of sight velocity. That's just the Doppler shift, right? It's supposed to be at 1420.4. It's not. That's because it's moving. You have the Doppler equation. I have it written on the right, but that's what that calculation is. So here with the sculptor, people are getting a line of sight velocity of about 230, 240. Now this next column here is distance. And this is a whole nother activity. In the Opus labs, it's all focused on the cosmic distance ladder. They learn how to use our Lyries and Cepheids and type 1As to get distance. So they've already had that lesson. So here I'm just giving you the best known distance using these kinds of techniques. For sculptor, it's 3.5 megaparsecs away, but like here's cigar, 3.65, surfboard, 8.8. You get the idea. But that can also be a whole exploration. Here I'm just giving you the distance. And well, the velocity divided by the distance is Hubble's constant. So you see what a lot of people did, sculptor, and you're getting Hubble's constants around 60. We'll come back and look at that. Okay, now stick in your edge frequency. This is a separate calculation. This is to figure out the mass of your galaxy. One edge or the other, it doesn't matter. Type in that edge frequency. And if you have a number that's widely different from your colleagues, then you probably measured the wrong feature. And some of these are difficult. And that's why I like using these spreadsheets in my class. And they also have trouble with calculations. So if they come up with something different, they go back and check their calculation, check their math, etc. Okay? But most of you are getting an edge velocity of 420. I'm just reading for sculptor. If you're on a different tab, you got something different. And Kevin, did you do sculptor or did you do a different galaxy? If you did a different galaxy, you might be on the wrong tab. That could explain your difference. And, yep, there we go. And anyway, that's the edge velocity. So the difference between the edge velocity and the line of sight velocity is the rotation velocity. Okay? And then, you know, to calculate, dig deep in your physical remembrance. To calculate enclosed mass, it's v squared r over g. So you just calculated v. The radius, Well, there are different ways to do this. Here I just gave it to you, but you could have your students take a picture with Skynet or LCO or anything and just measure. You use the measuring tool in Afterglow. You can easily measure the radius of an edge-on galaxy, just like you measure the distance between Neptune and Triton or between the double stars, and then do a small angle calculation. But in the interest of speed, I just gave you the physical size. And so this squared times that divided by g is the enclosed mass. You just weighed a galaxy. Sculptor came out around 10 to the 11. Let's see how some of the others look. Mid 10 to the 10s for the cigar. Surfboard, I'm getting like 6 times 10 to the, some are 10 to the 10, 10 to the 11. There's some variation here. But that was one of the difficult, we're into the 3 difficult ones. Hamburger, although a difficult one, you got consistency here. Needle, a little all over the place. But now back to the easy ones, and we're getting some consistency around 10 to the 11 or 9 times 10 to the 10. Crowbar, great consistency because only one person did it. Now let's look at these Hubble constants. Here's the median from each of you. 60, 40, 70, 70. Now from one galaxy, you're not going to get a great measure of the Hubble constant because there are things tugging on it. But if you look at the median of all those numbers or the average of all those numbers, yeah, we're not going to do Hubble tension with this kind of accuracy, but not bad. Again, the hard part of measuring Hubble's constant is measuring the distance. And earlier lessons, they learned that part of the aspect. Here, they're doing the spectroscopic, the redshift part. It's hard to get those in the optical on these kinds of systems, but really easy in the radio. So very nice Hubble's constant. Now, you want to do the Andromeda exercise to wrap it up? Okay. Now, Kevin, where are you, Kevin? Yeah. Kevin Lee. Yeah. So he invited me out to Nebraska to give a plenary at one of the education meetings. And I ended on this exercise because I thought it was so cool. And I just knew the crowd would go wild. And it was like crickets. I think I misjudged my audience. I think they're mostly physics high school teachers. And I didn't even get a question after that one. So we're going to see what happens here. Okay. One galaxy, as I said, our beam's 0.7 degrees. Every galaxy fits in it, and you do this kind of exercise. But there's one galaxy that's bigger than 0.7, other than our own. That's Andromeda. Andromeda is about 3 degrees across. Here, I'll bring up a little picture, because I'm sure you've never seen this before. There you go. There's Andromeda. I've actually rotated it into the RA-DEC coordinate system. And so it's bigger. We can actually resolve it. It's not going to be a pretty picture. It's going to be fuzzy, but we can do this through imaging instead of a straight-up spectrum. Now, one little caveat here with radio telescopes. This is a little fun aside, just to help increase your understanding of them. Now, I said it works like a prime focus telescope, but remember, the waves in this case are 21 centimeters long. There's not much room up there. You don't have room for like one detector element up there at the prime focus receiver. For you optical astronomers, think of it as a 1-pixel camera. You do in radio, you're working with a 1-pixel camera. So if you want to make an image, you have to move it around. You have to raster. And there are all sorts of technical difficulties that come in if you don't take all your pixels simultaneously. And we don't have time for that. But Skynet's really developed a very nice single dish algorithm. And it takes all the, what if someone blasts RFI as you're moving? What if the background is varying? What if by the time you get to the end of the map, it's setting and you're detecting the ground? All these things are in an automated way taken out. So the students get just a nice clean image with radio frequency interference removed. And so it's a whole nother workshop to teach you how to make these images. Instead, we're just going to go straight to the images. But here's the deal. As I think I've indicated, you can't not get a spectrum. Every point you take as you're rastering around, you got a spectrum. Now here's an on-off spectrum of the center of Andromeda. It's not the whole Andromeda. I can't get the whole thing in my beam, but just the center. So what do I have? Here's Andromeda. Notice the bumps on the other side of hydrogen because it's not moving away from us. It's moving towards us gravitational attraction. It is broadened a little bit, but it's actually even broader because I don't have the wings of the galaxy in here. But we're going to do a color image like we would in the optical. We try to tie radio to optical as much as possible because they have good intuition in the optical. So we can integrate up any frequency range after the fact. We don't have to image this 3 times with different filters. We have a full spectrum. So let's do an LRGB plus narrowband image, something astrophotographers do. For my luminance band, I'm going to integrate everything from here to here. This is the Milky Way hydrogen. We don't want that. So here to here, you can see the luminance band, the frequencies. And then I'm going to do the reddest third, which is the down here. And that would be my red layer. The middle third, that would be my green layer. And the high frequency third, that will be my, no, I got it, the high frequency third is blue. Yeah, right, sorry, brain fart. And then just for fun, often when you do an optical image, you do narrowband. Maybe you grab some H alpha. Well, let's grab H1. We'll pick a narrowband here around the Milky Way hydrogen. So I've done all that processing and I've stuck it in Afterglow. So here's how you get to it. Go to Afterglow. And doing all the processing is what takes the time. Putting it together into a color image goes pretty quick. And Daryl showed you how to make a color image in optical, but you didn't actually have the time to do it. Now we're going to do it. It's pretty quick. So everyone at Afterglow, okay, open files, and you're going to want to go to the sample space, down to the workshop, same as some of our previous workshops. So open, sample, workshop, and there'll be a folder called Andromeda. In there will be a single file. Go ahead and open it. And what this is it's already been set up as a multi-layer FITS file. It's a FITS file with multiple layers. And these are really tiny files, so they should load easily. In fact, I'm looking around, and everyone seems to have it up already. So let me show you what we have. This top one was that narrowband. That's just Milky Way gas. And we're in the Milky Way. We're looking out, so there are clouds of Milky Way gas all over the place. Next one down, called main 1, that's the luminance layer. And I said we would be able to resolve Andromeda, just barely. There it is, resolved. In the same way, isn't that cool? I find it cool. It's not like an optical image. You're not going to get the detail. But there's Andromeda in the same orientation as that picture I showed you. Right there. I'll put them side by side. 3 degrees across, optical and radio. Let's go down one. That's our blue channel. It's on one side of the galaxy. Here's our green channel. It's in the middle of the galaxy, as we've chosen the frequencies. And here's our red channel. Okay. So that's the side that's moving away. Well, because I said so. So I'm speeding the process up for you here. Basically, once your data comes back in Skynet, you can say, I'm making a map, but I only want the frequencies from here to here, or from here to here, from here to here. So I've done that for you. I stuck them all together, and I'm just letting you know. Let's color them. That will help you remember what's what. Let's start at the bottom. That bottom one is the red one. So right-click, color it red. Next one up, right-click, color it green. Next one up, right-click, color it blue. We could stop there and do a red, green, blue, but advanced astrophotography has a little bit more. Let's go up to the luminance layer. 2 things, color it gray. This is how luminance layers work. I'll explain it. And the second thing, right-click, go to blend mode, change it from screen to luminosity. The way a luminosity layer works, when you're doing astrophotography, if you have a layer with much greater signal to noise, you can take all your signal to noise from the luminance layer, and the color comes from whatever's beneath it in the list. So this will set the intensity The color will come from combining the three we just did, the red, green, blue. And the top one, let's turn it off just for a second. So you see that little eyeball? If you click on it, you can turn it off. Let's just do the LRGB, and then we'll throw in the Milky Way hydrogen for fun. Okay, I'll pause for a second, make sure everyone gets here. The bottom is red, green, blue, and then this one is gray, but we changed the blend mode to luminosity. Anyone need any help? The blend mode, you right click, and it's right below the color. There's the color, here's the blend mode. Yep. Okay, go ahead back to the top level. And if you want to fill the screen, this right here, this button down here, zoom to fit. Okay, so now we're at the top level. Go to your, and we're going to tweak this a little bit, make it nice. Go to your display settings. Again, you've been here before, it's this top button. Okay, and we're going to link them using percentile. Oh, sorry. First thing you want to go is select the luminance layer. So right here in this upper left box, select the luminance layer. It's the gray one. And we're going to link percentile to it. What this means is we don't have to adjust the red, the green, the blue separately. They're now all linked to the luminance layer. We just adjust the brightness and contrast of the luminance layer. The others will go along for the ride. Did you all follow? Good. Let's do it again. Display settings right here in the upper right. Okay? In the first box on the left, we're going to pick the luminance layer. It's the gray one here. Okay? And then we're going to link all layers percentile. It links all the layers to the luminance layer. We're going to walk around the room and make sure you got this. Nothing will change yet. But already it's cool. Once you, for those of you who did it, you can start playing with the saturation level. Down here at the saturation level, you can play with the arrows. I'm going to increase mine a little bit. Get it as you want it. But I'm just controlling the brightness and contrast of the luminance level. Everything else is going for the ride. Maybe I'll set it to bright target. That's pretty good. Are we all linked up? Anyone need help? First, select the luminance layer. Oh, click on the top of the group, sorry.
This
Yep, okay.
okay.
Now you can pick the luminance layer, the gray one, yep. Color composite, link it percentile, yep. And now everything's under the luminance control. You can play with the settings here, either the coarse settings or the fine settings. But like, basically this setting here, your saturation, it will work. I find bright target's pretty good for this data set. Just whatever looks good for you. I like to go up a little bit so it doesn't look so blobby. The blobby is the name of the game with single dish radio telescopes. I'll let you get this nice and neat.
You mentioned
Yeah, keep it off for the time being. Go back to the main top layer.
this one.
Yep.
Oh, here.
Now
okay.
display settings. First click on this on the left. Select.
Gray.
Oh, I'm sorry. Select main one. Main one, the
Main
second
one.
gray.
Yeah.
Okay, and then link percentile. I'm sorry. I had already colored my my Milky Way hydrogen. So when I came here, oh no, yours was colored too. Yeah, everything's fine. Okay, maybe try bright target. You can adjust, try like bright target here. You can adjust the brightness and contrast. If you go down to the saturation level, you can fine tune it. Everyone good? Everyone got a nice red, green, blue separation? Okay, last little bit. And this is just for fun, to put it in some context. Go ahead and turn on the Milky Way hydrogen. The first layer, main one, we had turned it off. Looks ugly, it doesn't look right at the moment. We got to give it a color. Let's color it Bomber. Bomber is what we color H alpha in the optical. This is not H alpha. This is not an optical image, but we're kind of treating it the same. I'm just going to color mine Bomber. And I'll show you how to adjust that in a second. But turn on that first layer, which is the Milky Way hydrogen. Give it a color. If you don't like Bomber, pick another color. Pick a color you like. And for me, it looks a little faint. I want to bring it out. So everyone here? Everyone's turned on their, okay. Just come up here to the top. Select the brightness and contrast controls for that layer. For me, it's Bomber colored. And once you do that, you see it's currently linked. We linked everything to main one. Come down here to this linking and put it back in manual mode. And then you can control it separately. You can play with that saturation level. I'm going to bring mine up a little bit. Whatever makes you happy. Maybe the stretch mode. Maybe I'll change the stretch mode to midtone. Hit default. Yeah, I like that a little bit better. Anyway, you have a lot of freedom. Whether you want to change different stretch modes, you change the saturation level. This is exactly what you would do in an optical image as well. If you want to bring out the H alpha in a star forming region. Yeah. Okay, so go up here, change to the Bomber control, unlink it from the main, and now you can control it separately from the rest. Anyway, that's basically the idea here. Students can go, as you imagine, based upon the choices of the filters. They have the central frequency, so they can calculate how fast it's coming towards us, the collision timescale with our galaxy. And from the frequencies for the red and blue filters, they can figure out the rotation of Andromeda, the enclosed mass. In fact, to calculate enclosed mass, it's v squared r divided by g. I'll go to the plotting tool. There, I can measure the size using the plotting tool, the angular size. If I know the distance away, there's my r. So, there's additional layers you can build into this, but lack of time. Questions?
Galaxy disappeared.
Go back to the top layer. You're just looking at the,
Oh.
yep, and you can zoom out and stuff like that. It's all there. I don't know. Am I going to get crickets on this one, or does this excite you, being able to see Andromeda rotating? It's pretty cool. It's pretty cool, actually visualizing the rotation of a galaxy.
Sample the spectrum to generate?
Yes, the instructions are right at the top of that section of the tiny URL. There's a whole manual. You can go through this. In the manual, it does Andromeda first, and then the more distant galaxies second. Any other questions on this workshop? Are you starting to believe that radio is cool? Are you starting to believe it's useful? Great physical concepts. Okay, so be open to radio in the future. Let's pull up the schedule. We are at 5:08.